My name is Henrik Madsen. I'm a professor in statistics at the Department of Applied Mathematics and Computer Science at the Technical University of Denmark, near Copenhagen. Today, in 2019, on average roughly 50% of the electricity is generated as wind and solar power in Denmark. Wind power alone accounts for around 43% of the electricity load, but this is highly fluctuating. We have hours with almost no wind, and on the other hand, we have seen periods with up to 140% of the electricity load. This implies that forecasting is crucial in order to operate the energy systems, including the electricity grid. I have been involved in renewable energy forecasting since the early 90s, when the wind power took off in Denmark. The lessons learned over almost 3 decades of wind power forecasting is that the optimal tool for forecasting depends on the level of wind power penetration into the power system. I would say that for 5 to 10% of wind or solar power, point forecasts can be sufficient. Point forecasts provide only a single number for each future time point. This means that no information is given about the uncertainty of the forecasts. For 10 to 20% wind or solar power penetration, probabilistic forecasts are important. Probabilistic forecasts provide information about the uncertainty of the forecast. Without proper methods for probabilistic forecast, there is a high risk for curtailments and hence for losing the green power at hand. Obviously, this again has economical consequences. Let us briefly mention some of the most important theoretical facts related to wind and solar power forecasting. Forecast errors related to wind and solar power are not Gaussian. This is seen on the figure, for instance, by the fact that the prediction intervals are non-symmetric. Gaussian distributions are symmetrical. This implies that tools building directly on this assumption are far from being optimal. Furthermore, it's well known that the width of prediction intervals for linear models, like Box-Jenkins, ARMA, Hall-Winter, etc., is never decreasing. See, for instance, my book on time series analysis for an introduction to these models. But as seen on the figure, the width of the prediction intervals can decrease locally in time with increasing horizons. Consequently, direct use of linear models for wind and solar forecasting is suboptimal. In the following lectures, we will see that good forecast can be provided by using proper mathematical transformation in combination with nonlinear models. Forecasts are typically needed on different timescales, from minutes, maybe even seconds, to days. Furthermore, forecasts are needed for single turbines over wind farms to large bidding zones. For large-scale integration of renewables, forecasting on all temporal spatial resolutions are typically needed. Good meteorological forecasts are very important in order to obtain good wind and solar power forecasts. Sometimes it can be a challenge to obtain good forecasts of, for instance, a split between direct and directional dependent diffuse shortwave solar radiation. Therefore, it's advantageous when the provider of the tools for renewable forecasting has a good collaboration with various providers of meteorological or MET forecasts. Today, MET forecasts are typically either cheap or even free, and since it's well known that different providers are best for different horizons, etc., it's also advantageous to use forecast tools which are able to take advantage of several MET forecast providers. As an integrated part of a good wind and solar power forecasting tool, the best combination of MET providers is found by use of technologies like artificial intelligence. With more than 20% wind or solar integration, then energy systems integration becomes important in order to unlock the flexibility needed for an efficient integration of the renewables. Furthermore, the forecasts have to be fully stochastic. This means that also the expected time dependency or autocorrelation of the future forecast errors are taken into account. This time dependency can be described by using covariance matrices after a proper transformation of the numbers such that they somehow resemble a Gaussian density. A more robust and powerful method would be to use stochastic differential equations, and we'll come back to this in lesson number 3. All information related to point, probabilistic, and time dependency can be represented and illustrated by forecasted scenarios. Such scenarios are useful as input for optimization and decision making, and for instance for use in stochastic programming. With more than 20 to 30% of wind or solar power integration, forecast of flexibility of the load due to the critical need for demand response will be essential. Efficient methods for describing and utilizing this flexibility are important, and we'll come back to this in the second half of this module. It's very important to use a forecast provider which is able to generate joint forecasts of wind and solar power generation, and jointly with load and eventually also price forecasts. If you get tools from different providers, then the representation, for instance the sampling time, resolution, etc., is typically different, and most importantly, it will be difficult to obtain a proper cross-dependency between various energy components. This implies that the total forecast setup will not be adequate. Furthermore, it will be difficult to use all the forecasts in the tool for optimization and decision making. This is, of course, very important in order to be able to get the optimal economical benefits of the forecasts and a robust operation of the energy systems.